Okay, thank you for the opportunity. And let me first set expectations. Unlike Professor Yanni's talk, which was full of very exciting new mathematical results, this will be an applied talk. So there will be here and there some fairly trivial exercise level propositions bandied about. But on the whole, it is more about taking an engineering approach to these things than about discovering some new and exciting mathematics. I think all the mathematical tools that one needs to do this kind of things are already known. So this does not require exciting new mathematics. It does require cutting back on some ambitions. I will be talking about what is it that you cannot do in order to do some other stuff. So there are trade-offs. That's mostly what the talk is about. In the background, this wouldn't be 2026 if we could give a talk without machine learning and large language models, and this is increasingly impossible. But as far as logic is concerned, and compared to machine learning, these two fields are very, very different. I tried to list some of the characteristic differences here. First of all, logic is typically operating on discrete units, whereas machine learning likes a continuous setup. And accordingly, the mathematics associated to logic is algebra-like, basically. And the mathematics associated to machine learning is typically like calculus. There is a continuous stats, there is differentiation, there is gradient descent going on, all this kind of stuff. Okay, statistics. Logicians, it's irrelevant. There is no such thing as statistically proving something. No. This is machine learning is the key and absolutely indispensable tool in machine learning. There is no really many people will tell you that machine learning is just one chapter of statistics. It's a fair thing to say. Types. In logic, proof theory in particular, these are the load-bearing elements in many ways. The type system, you have a proof system, you can get going. In machine learning, types are vestigial at best. They are really, only on the periphery of thinking about machine learning problems. And subdomains. Subdomains are things that the logicians like. The logicians like to say that, okay, we have this bit of temporal logic here, we have this bit of epistemic logic here, we have this thing, we have that thing. They like to have very detailed work, a sort of mosaic-like putting together of a lot of theories, maybe parametric families of theories actually, that address different subdomains. In machine learning, this is hated with an intensity that is very hard to describe. It's that you go to a machine learning guy and say that you can do this here, but you cannot do anything anywhere else. You're basically tossed out of the room. They don't want to hear about you. They basically think that the one thing that happened in artificial intelligence that is sort of not the technical development, but sort of the psychological development, is that instead of AI, now we are talking about AGI, artificial general intelligence. You really want the general, all-encompassing theory. You don't want to do something that's only good for vision or only good for natural language or any of your favorite machine learning areas. You want something that works everywhere, okay? That's where the real interest is. Okay, so nevertheless, there have been efforts at synthesis, and one of them is Markov logic by Richardson and Pedro Domingos from 2006, and then later by Domingos and other co-workers. And the problem with this is it didn't have really strong logic flavor. Okay, it was sort of machine learning moved from one particular domain, string domain, to more like a tree domain. But essentially, it didn't have a very strong logic flavor. And there are Domingos didn't give up, and neither have I must say. So we started to do two things. I started to do something called vector semantics, and he started to do something called tensor logic. Okay, and there's a book and there is this paper, and the hope is that these may fare better in terms of bringing these two areas together. And this talk is planned to describe the current state of overlap, which is really too small for everybody's good, either on the machine learning side or on the logic side, and suggest some directions for hybrid systems that are more perhaps show better learning characteristics than the current ones, and maybe even on the logic side have not necessarily mathematical novelty, but the novelty of being applicable. Okay, to some people this matters. So the logic, this is a historical accident that somehow the syntax of logic was created before the mathematics of syntax was created. So this was just tossed together by very competent mathematicians at the time, but without too much thought for how language in general works. And the really painful aspects are that there are two infinite vocabularies for variables and for extra logical constants. And you don't want this. I will get into more detail on this. There is terminal vocabulary, what in formal language theory we call the terminal vocabulary. They will have the parentheses, the quantifiers, the Boolean operators. You have stuff that basically unique, plays an important role in the syntax. These are roughly what sort of the medieval logic tradition considered the syncategoremata, things without categories, right? As opposed to the nominally definable stuff. Okay, then you build terms, you build formulas, and basically there are, why is reset? Why not answer? Because 3-set is already very hard. As a sort of combinatorial problem, it's already very, very hard. And we have first order logic, higher order logic. You can describe now the syntax, given what we said so far, pretty easily using very standard formal language theory type methods, and ask the kind of questions that Chomsky started to ask about natural languages, not so much about formal languages, of the strengths of the syntax of these various things. And what we know are the following, is that first of all, the syntax, whether a formula or a proof is well formed, okay, that fits well within the so-called context sensitive or L1 family in the Chomsky hierarchy, okay? And natural language, turns out it fits into an almost context-free family called the mildly context-sensitive family, which we owe to Aravind Joshi and his students. So this, Chomsky was not cognizant of this, so he had L1 for context-sensitive and L2 for context-free, and now we have L1.5 for these intermediary things, okay? And there is this conjecture by Marsh and Party from '84 that logical syntax will fit there too. Actually, they frame the conjecture in the negative. They don't know. This is really a conjecture, and since it was in '84, this is now by far the greatest upstanding problem in formal language theory. It's been 40 years that this has been posed, and nobody could say anything smart about this. Okay, so in the vector semantics thingy, there are only two variables which correspond to the grammatical agent and patient, or if you wild the case endings, the nominative and accusative case endings. Anybody who does Latin and maybe even Russian, these kind of languages that have them. Okay, Hungarian is good for this purpose. Okay, and we only require a finite number of constants. This is worth hammering. It's a ballpark, maybe 100,000 constants. Roughly each word you want to be a constant, and there aren't that many words. There's a finite brain capacity. You only know a finite amount of words. Okay, so if you compare this to Tarski and Given, who with 3 quantifiers already gave very decent formulation of both set theory, you know, various flavors of set theory, and piano axioms. So arithmetic, you could do arithmetic, you could do set theory once you allow yourself 3 of these guys. Well, if you allow only 2, maybe the answer is the negative. You cannot quite do this, okay? This is the biggest trade-off that we will do here. The plural, it's not just me, right? I'm a maniac. I sort of insist on natural language being an important domain, and, you know, mathematical linguists are few and far between, and they all insist, but it's actually a small minority. Nevertheless, it's not just me. We want to do things that way. We'd rather give up arithmetic than give up natural language. Okay, so this is a big trade-off, and mathematicians, mathematically trained people, 99% of logicians we're talking here, they hate this. They don't like this really that much. If you give up arithmetic, they feel that they have been they have been, I don't know, cut off at the foot or something. There's something really, really bad here going on. If you look at the LLMs are actually this. Okay, they are very, very good about natural language. You can devise all kinds of tests that show that they are good, even better than you originally thought, and they are still improving. And sort of, you want try to do elementary arithmetic, them, you know, multiply 2-digit numbers. They suck. Okay, they really don't know how to do simple arithmetic stuff. So it is this side of the trade-off that we are interested in. We are interested in LLMs. It's 2025. This is okay. It's like pulling teeth, but you have to give up on this piano axioms. Okay, not on the axioms and not on the study of arithmetic. That's not what I'm saying. But you sort of don't see systems anywhere on the horizons that would be capable of machine learning arithmetic. And actually, I'm running experiments with people at the Rainy Institute and elsewhere to have LLMs learn simple sublanguages pertaining to arithmetic and logic, and it's hard. Trust me, it's not trivial. Okay, so once you admit these limitations, that you don't need these infinite vocabularies, you need only this tiny sets, then turns out that there is no Marsh-Party conjecture one way or another. A little thought will show that you can do everything with a context-free syntax. Okay, so really the problem is posed by because you need this infinite number of variables, and to have the infinite number of variables, you need to somehow index them, and to index them, you really need an arithmetic. And once you give up on this indexing them and doing it that way, and you only have a finitely many to begin with, the problem goes away. Okay, so the semantics, the big common point between the machine learning and the logic community, I would say, is that you can do this with 2-valued logic throughout. You don't need to invoke. There is a lot of other things that, you know, fuzzy logic, this, that, and I'm not trying to be negative about them. All I'm trying to say is that you can get everything accomplished by using 2-valued logic through and through. Now, the basic theory is reist, not realist, it's reist. It is, the notion is that the worlds are composed of objects and their relations, and these are really the sort of standard Tarski-style semantics story with a bit of enhancement from Kripke. We just look at to see what is true, and we look at satisfaction in models. And to do the model logic, you actually look at nearby models as well to figure out what's going on. The ontology, again, since we don't have too many things that are infinite anywhere, really any usual variant of set theory is fine. You don't need to sort of tie yourself into foundational knots to get stuff done. Okay, so here we will make use of Karl Popper made this distinction between clouds and clocks. It's a very good name. I really like the whole metaphor. What are the clouds? The clouds are point clouds. They are finite samples from possibly infinite distributions in multilinear space. Okay? Point clouds. You see them anywhere where measurements are taken. Okay? There isn't one branch of engineering or physics or anything like that where you don't encounter these point clouds. Okay? And they are really the ones that we want to handle for extra logical constants. And the big thrust of this is how do you going to make these two come together? You enlarge the domain of logic to do a little bit more by logic than what you used to be able to do. And instead of a few logical constants, which are the Boolean operators and the term binding operators and these kinds of things, we want to do as much by logic as we can. So you now have, like, you know, a logic of tense, a logic of time, but you don't necessarily have a logic of verticality. And the claim is that you can have one. You can do stuff by logic, even when you define things like choose, okay, or vertical. You don't want an extra logical treatment. You want a logical treatment for this, okay? And the clocks will be model structures with one really important twist, that they will come endowed with automata theoretic transitions, and also possibly I/O. I will be talking a little bit about the I/O, but the main things are the transitions, that there is a transition structure across the points of the model, okay? So what we want to turn certain key notions from extra-logical to logic internal. One of the key notions is life, to be alive, living in any morphological form you care to say this. This is something that we want to move from the extra-logical domain to the logical domain. So you want to talk about the logic of life. We haven't done much of that before, okay? And we begin with a very modest goal. We take these model structures, and we want automata to live there, okay? The typical automaton you have to think of is your ordinary computer, laptop, whatnot, okay? You don't need some very special notion of automata. And the typical model structure is this raised, space. Think of the region of space where atoms are arranged to form what we recognize as a server room. Okay, so the computer sits in the server room, but there is one interesting thing between these two, that in 1 second, the server room, it really doesn't change much. Okay, it's pretty much as it was. Nevertheless, your computer performs several billion operations, gigahertz speeds. So there is this very, so we will introduce a notion of time scales to handle this. And this is the one big change compared to what people have done before. I think I'm good on time. I'm going to do the temporal logic and the party paradox. Who has seen this party paradox before? It's simply the sentence, the temperature is 90 Fahrenheit and rising. Okay, everybody can see the paradox, right? It's by transitivity, if the temperature is 90 and the temperature is rising, then you must conclude that 90 is rising. Okay, well, 90 does not rise as far as we are concerned, so there is something going on here. You need to handle somehow this kind of pesky ability to coordinate this stuff and make these kind of predications about them. Okay, so the standard solution comes from Richard Montague, who simply considers temperature to be an intentional noun which can take different values in different possible worlds, right? So it's a function, and if your temporal succession gives you the possible worlds, it will take on different values in different possible worlds. And then really there is Montague grammar, which tries to address not just this, but several classical problems of how to translate English to logical formulas. And his student Dan Gallin actually published a much more detailed thing about this than Montague, whose life was cut short by murder fairly early. Probably he would have gone on and done wonderful things. The models are typically indexed by ST pairs, but the time T parameter is already factored out from the others, right? And the use, at least in the original literature, the use of such indexes is abstract. There is no structure. You don't say that T, the temporal index, is structured as the real numbers or as a discrete sequence. It's just some kind of abstract thing. So the explicit temporal order begins with Barbara Partee, and Hans Kamp worked a lot on this, and Reinhard Muskans, and they sort of distilled this down to all sorts of linear orders are good as long as precedence is compatible with containment. And we will be even more general than that, because we will treatment things like frequentatives, like Hungarian got-get, so as in isogot. It doesn't mean that he drinks all the time, and doesn't mean never drinks. It means that he drinks regularly, okay? Ígérget, regularly makes promises, these kind of things. Now, it takes an effort to treat these as unique things, okay? But if you think of odd numbers versus even numbers, okay? This is the same kind of story, that they come, an odd number will be followed by an even number, again will be followed by an odd number. It is the single most natural structure whereby you can describe these things is a cyclic group of two elements, right? It's just like day and night. Okay. And there is some discussion in an earlier paper of mine on how you can build much more complex ones than these, just based on this. I'm not going to get into that here. So vector cement, how am I doing on time?
You have about 5 minutes and 5 seconds.
Okay. So we consider individual samples, which are occurrences in text of words like vertical or choose, and these are the ones that give you your point cloud, okay? And once you have a point cloud in the space of word vectors, then you can, if it's very tight, you can just characterize them by their center, okay? Think of it as a probability distribution. The mean is a simple but very effective characterization, okay? More typical is that you want a bounding polytope around it. That's very often the boundary hyperplanes correspond to well-known and well-understood things. So, you know, there is a predicate that, I don't know, featherless, just to use some classical example, either something has feathers or it doesn't have feathers. So featherless sort of sorts the world into two, you know, to the left or to the right of this hyperplane. And if you say that humans are featherless bipeds, okay, then you use these to characterize how you do this is can discuss this. Okay, protopes are related to one another. So the vertical, this is defined here as direction. It has a top, it has a middle, it has a bottom. Earth pull in direction, in the vertical direction, right? Notice that this has immense survival value. Ever since we've been monkeys on the tree, it was really good to know which way is up and which way is down. Okay? So much survival value that this has long, basically 500 million years before humans or vertebrae. This was already relevant. You know, mollusks already detect the gravity vertical. Okay, so here's the definition of choose. Choose means X choose Y means X chooses Y for X. I'm not going to go into the details of this, I could, but basically there is a formulaic definition of the notion of choose that is not any different from the way you would want to do formulaic definition of anything. Okay? Such definitions are circular. Each provides an equation in a small system of equations. And there are less than 20 true primitives. A lot of old efforts went back trying to sort of trace down definition and then substitute whatever was in the right-hand side by its definition and so on and so forth. And you cannot do that. You have to, again, admit a bit of circularity here. And to get to the vectors, we solved in the vector semantic system, you solve the system of equations. Okay? This is not as good as learning them. Although the mathematics of the two are surprisingly similar, of course, because equation systems of this side you also solve by gradient. This is not by direct substitution techniques. But nevertheless, you really want to learn them. That's much better. So the tensor semantics, instead of the formulas, the basic units of the formal theory are tensors of arbitrary shape d1, dk. Okay? K-dimensional, I don't know, matrix. And these are used both to model specific entries and to select particular indexable subsets of model structures. So you use it both places. Okay? There's an existential cut here. The boy ate as a sandwich. It's meaningful only in worlds where there are boys and sandwiches. Okay, so ancient Greece, how much we like it, they didn't have sandwiches. They had boys, but they didn't have sandwiches. So you couldn't even make sense of the sentence there, okay? Okay, a neighborhood of worlds is selected around the here and now point in index space. It's not just a single point. It's actually a small neighborhood. Relation composition is done by tensor multiplication. And Domingos does another very exciting thing. Once you've learned something, he has this notion, very important in AI for the past 30 years, of predicate invention. You want to be able to introduce new relations. Okay? How do you do that? You do this by learning from instances. You basically generate a small convex hull around your data points, data clouds, okay? And he does this by thresholding. So everything for which the coordinates are greater than 0.5 is in, everything that are smaller are out. Okay. Whether this is the right way, there could be other ways of doing this. That remains to be seen, but there's no doubt that the ability to devise new predicates is key to human performance. Humans are doing these things very well. Okay, we want these AGIs to also do them well. Automata. I have a few minutes, okay. Automata, we use more automata. There's a paper that I will basically just advise people to read this. This is an archive. But the last point I'm going to hammer a little bit, that automata are models and models are automata. We don't make a huge distinction between these two classes of objects. Labels and symbols. there are specific restrictions which sound very strange to mathematicians. Okay, engineers, they just, say sure. But mathematicians, it drives them crazy that you can have a finite alphabet and it cannot be bigger than 256 elements. Okay? Why not? Why not? Why not? You really don't want to and you really don't need to. Okay? So, and there is empirical evidence actually, interestingly, that within the human synapses there's only 4.7 bits, transmitted. And there's actually theoretical work says that only 2 bits are transmitted, but the sort of computational neuroscience work is now, at 4.7. So I would like to say that the binary alphabet 0, 1 is created by God, and the rest are the work of man. Okay, so the clustered Moore automata, there is this paper, and at the end of these slides, there is actually a detailed list of references where you find the paper. The one thing I want to mention here is that under realistic assumptions, this cannot be built up to be full Turing machines. Okay, although Domingos believes that, and Hava Siegelman, a smart woman, also believes that. But if you look at this paper by Weiss, Goldberg, and Yahav, you will see that you cannot, on the realistic assumption, you cannot get. Why cannot you? Because every time you embed a loop within a loop within a loop within a loop, you need more and more and more machine precision. And this you cannot do, okay? So what the automata get us, okay, I'm going to skip this. I'm going to skip the clustered Moore automata. Say maybe something about the party paradox. You can see how this will work out, actually. The point is that you are in this server's room that runs in a slow time scale, but inside there are states, and each state can hold a smaller automaton that runs on a much faster scale. And this goes on not quite recursively. Again, this has to terminate in a finite number of sets so that between the top time scale and the bottom one, there is only a finite number, okay? So it's not like hereditary finite where it can be arbitrary long descending chains. Here you cannot have that, okay? You can only have, chains of at most 18 or whatever, even less. Turns out that 3 is a good number here. Okay. Okay. So here's the automata living on the model structures. This is again worth emphasizing. How you do this on actual physical computers? You have a time signal. You have a clock signal that goes out to every transistor, really, and you synchronize the motions. Anybody who programs on CUDA? Anybody here who does any kind of machine learning? Raise your hands, raise your hands. I'm sorry?
H trees.
Okay. So these are amorphly times. There is no synchrony anywhere assumed in advance. Okay. Everything is infinitary, everything is discrete, but it looks as if it was infinitely continuous, and this is because the structure is set up so that the sort of the resolution of the system with each layer you add, it grows tetrationally. So it really goes fast. And by the time you are at layer 7, it has so much stuff that you really don't need anymore. Okay. And let me close on this great quote from Kronecker, who is asking Lindemann, really, this happened, of what use is your beautiful investigation regarding pi? Why study these problems when irrational numbers do not even exist? Okay, so thank you very much.